हेलो। हाँ हाँ, कौन बोल रहा है? हेलो। अच्छा संदीप, अच्छा हाँ हाँ संदीप, मैं थोड़ा क्लास ले रहा हूँ, मैं कॉल करता हूँ तुमको। हाँ, नहीं 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 यार, वो 7 से 9 क्लास है। करता हूँ। I was waiting for everyone to come. But still, it's nobody. I will start the session. Otherwise, I will take the lecture. Hello, good evening. 6 assignment is about FEM. Is it about FEM? It is evaluated. I evaluated yours also. I remember. Yeah. Okay. Your marks are still not shown. Okay. I have evaluated it. Maybe it will be. So for others, it is shown or not? Hello, Kapil. I can't hear you. Yeah. Good. What you were saying? For others, it is showing or most probably I checked your copy, so it is fine. I think it will be uploaded soon. But I think I have evaluated all the sections there. Let me check, but I have to. Okay, this screen is not shared. Okay, I am checking. Actually, my screen is recording. I can't do it. Later, I will do it and let you know. Most probably, it is checked, and I, I'll I evaluated your copy. I think your submission means document, and I think it was fine. There was some mistake. I pointed it out for everyone. I gave some current comments there, and it's fine. I think it will be shown in some days. Kripal, hello. Uh, yeah, your marks are shown in for assignment 6, not visible. For everyone, Apurv, it is not visible. For him also, it is same. Means no. It is evaluated on the basis of solutions. Are you getting solutions or not? Derivation, yeah. 6-1 was derivation. Mm. Yeah. So if you submitted it, then it will be shown in some days. Means I didn't get it. Typical values. There are no typical. It depends on problem. So it totally depends on the problem. There is no typical values actually. It's a stream function, so you just take it, and based on that you based on the problem, there are values of that. So if you are getting some other higher values, then there is some problem in your code. It is not like that. Most of the time it is not like that. Assignment 7 you are asking. Okay, let me check it. I actually don't know about assignment 7, but I have to. Yes, yes. No, you should not get very high values. You should be between the like between the boundary conditions sometimes, and it depends on the source term. So I have to solve it. You got some code with it for for assignment 7 you got some code. No. I am just asking. You got some code from our side or not for assignment 7? You didn't get. You got the problem. Okay. Actually, in assignment 5 there was a problem with for lot of students. I don't know about you and Apu, but others there was a problem that they just copy pasted the code and in the uh, log file and submitted. So if you just copy paste the code, how will I give marks? I don't know. And some I know you have submitted, but I am just pointing out to others also. If anybody is watching this recording, so for them I am asking that why they have submitted this code, because there is no point of submitting that code. I have given marks to that those persons, but there is no point of giving such type of codes, because you are not learning anything, you are just copy pasting source code and submitting. So you should at least either run that code or move to other coding language and take inspiration from this code. Like if you want to explain someone that code to you, you just copy paste that code to chat gpt, it will explain you, and then you can move forward for other language with whatever language you know, and then submit it. That will be better, I think. And then for post processing thing, I think 4 or 5 people have done only post processing of that spiral thing. It's so what's the problem? I don't know. It's a coding problem, or why you guys are not able to submit? Like you are also facing some problem while doing assignments. Uh, Kripal and Apur, anyone can answer that. Are you getting any problem while doing assignments? Yeah, yeah, as you pointed out. Mm, range of values. Yeah. Look, like if no energy is being created, you should have to understand that if no energy is being created inside, means no source term is there, then there should be, the value should be, suppose here temperature is 500, there is a rod, and in that rod, uh, suppose this is a rod, and in that rod here temperature is 500, where it is 1000. So if there is nothing producing inside, the temperature will be between that. So same concept apply to other values also. So I think whatever you are getting is somewhat wrong, or some integer or real kind of problem you are facing in the coding. Most probably it is like that. Somewhere you are dividing with 0 sometimes, and so if you are dividing with, you just look at it. If you are dividing it with 0, just replace it with 1 into 10 to the power minus 6, 1e minus 6 kind of thing. And if some error is enhancing in the loop, then also it can be. You have to check it. You have to debug it. Go section by section. And if you are doing, Kripal, are you doing it in MATLAB? Okay. Actually, problem is I can't help before that. But yeah, if you tell me the problem exactly, then I will be able to do it. Most probably a bit. Just wait. I'll share the assignment, and then are you able to see the screen? Here in this assignment, upper plate and lower plate are fixed, and balance. Okay, these are the boundary conditions. Yes. What's the problem? Okay, you are saying this. Apur, actually, I am just looking at this problem for the first time. So, Apur, can you help him a bit, if possible, in the problem understanding? Okay, okay. Actually, the problem is okay. Mhm. No, the problem is like that only. The problem is the boundary conditions are defined like that. That's fine. The values he is asking, the problem is totally fine. It's there is no problem in like defining the problem. That I know. Okay, let me just give me few seconds. I'll go to my other computer and look into it. Here the problem is I can't share everything. I look at the problem when I go for evaluation. So I didn't look at it till now. I looked till week 6. I think there is something missing. Whatever you are saying, according to that, if something is missing, I will upload it. Yeah. Okay. Just I am just looking at this problem. Just wait for a few seconds. Okay. Whatever I am getting is those values are really not needed. I will share if I get something for that problem. I will look into it. Today, this time, problem is with me. I didn't get much time for these problems. So, formulation. Formulation, I think you have already done. Boundary condition. There's no need, I think. As far as I am looking at this, I am not feeling any need of defining 5n. But yeah, I have to look into the problem properly, then I can tell you. I haven't looked into it properly. It will take some time for me to. Not easily available. Okay. Sir is really busy actually. I asked him for some one of the student actually asked for some material to solve the assignments and everything. But when I asked sir, he was actually really busy. So I had to download the material and share it with him. Try Sci-Hub. It's a illegal kind of thing, but yeah, you can try it. Sci-Hub, SCIHUB, Sci-Hub. So there you just paste the name of research paper and you will most probably you will get it. Sometimes it is not freely available. So can you share the name of research paper in the chat box right now? What I will do, I will download and. Mhm. So today, I want to take the staggered grid arrangement problem. So okay, Apoor shared it. Numerical solution. Physics of fluid. Okay, I'll share it. Yeah, I got the PDF. Apoor. So I'll share my screen first. Yes, no, actually I can download it. It's in IIT. It is freely available. So this is the paper, I think, from and Harlow. Can you see my screen, Apurva? Okay. So this is the paper from physics from and Harlow. No, I'll download and supply it to you. There is no point. Like there is no need of you to download it. Right now, I will do it. I have uploaded it. Can you check? on this my drive, whichever I have shared with all of you. Chetan, oh sorry, Kripal, Krishna, you can also check and let me know that you got it. Yes, Krishna. Krishna, you are, you can directly ask. I have shared in this CFD and heat transfer uh, that in which you get your class notes, the same folder. You have this? It's there? Okay, okay. You can download now. Others also, if you want, you can let me know and I'll provide. So let's start our class a bit. Uh, Kripal, I will let you know about that. If like in most probably in one day or 2 day till Sunday, I will. What is your assignment submission day? It's 13. 13 20th. Okay, it's submission date is over. You mailed me. Okay, I didn't get your mail. Mm, if I get any mail, I will reply sometimes. So yeah, I can't open it right now, but yeah, I didn't get. So you ask in that section some, like if you get any query in the discussion forum, you ask. Yeah, like if there is a like personal thing with me, like you want to ask particular thing, then you can ask me on that. So this is my email ID. I didn't get it. Sorry, Papa. So yeah, like while checking, I will look into your problem. If there is not a big issue, I will give marks. Don't take tension about it. So I mostly look at the code. Algorithm is correct. Then if algorithm is correct, then I'll go for good marks. If there is no algorithm, only some wrong, then low marks I'll give. So this is my strategy of giving marks. So mostly, like personally me, there is one other person who is checking those documents. So I will look into uh, the problems, like the algorithm. If algorithm is correct, then I am fine, totally fine. And output sometimes it will not get it. But yeah, if you've applied a good algorithm. So this week 7 assignment, in that also you have to write something and then apply that. It means algorithm and then apply to any coding language. So what I am thinking is taking the full solution of Navier-Stokes equation in these classes, so that you guys will be able to code the Navier-Stokes equation solution. So for that, today I am taking staggered grid arrangement problem. What is a staggered grid, where we use it, and why we are using it. So have you guys listened about artificial viscosity problem or artificial viscosity solution? Sir taught in the class he taught. Okay, okay. So you understood it? Okay, okay. So we will start with that coding for that problem, and then next I will go for simple algorithm coding in MATLAB, so that it will be a base for you guys for next assignment. I think next assignment will be based on Mac algorithm, because week 9 is, I think week 8 or week 9 is Mac algorithm thing. 9 9 is Mac algorithm. Okay, so yeah, so week 9, so it will be used in week 9 and week 10's. Week 10 10's assignment is, yeah, week 11 week 12 will be totally turbulent flow based assignments. So yeah, you will get, yeah, CFT Mac algorithm will be week 9. It's, I uploaded it today only, that week 9 thing, and you got that assignment, same similar, but it's based on marker and cell. Uh, so yeah, this week 9 you will understand that. Next week, yeah, so till next week, next week will be week 9. Week 9 I will take the Navier-Stokes equation by solution of Navier-Stokes equation by this artificial viscosity method. So today I will explain some bit theory about it. So others who are watching, if they don't know about the staggered grid, if they don't know about the artificial viscosity, why we are using it, why, how that pressure thing is applied, and how the equation is discretized, and how those values will be taken in MATLAB. So I will tell in according to MATLAB if you are using. So the difference is, when you are taking it in MATLAB, the array index will start from 1, but if you are taking in C++, it will start from 0. If you are taking in Python, it has some other effect. If in Fortran, it start from 1. So in every language this indexing is different. You have to look into it, and accordingly you have to define your problem. So there is a problem of lid driven cavity. So this lid driven cavity is the basic problem for most of the CFT, you can say softwares, you can say for coding languages also. So this lid driven cavity they take as a first problem, understand that, and it mostly used for test case also, like, is my algorithm is working fine, is my solver is working fine. For that also we take the lid driven cavity problem and understand the CFD thing there. So this is the problem actually. So in this these three sites boundary condition, it's similar to the assignments, so that is why also I have taken this problem. In this you will understand how to visualize also. So this problem I have done in open form for simplicity. You are not allowed to do it, so you have to do it in a coding, any coding language, so that you will learn. But so this open form is a open source software for CFD, in which in background we are solving different type of algorithms. So here this problem is solved based on simple algorithm, and simple algorithm is another way of solving the pressure linked, pressure coupled, pressure velocity coupled equations. So here you can see, as we analyze the this problem, so here in this boundary the velocity is 0, in this boundary this is treated as wall and velocity is 0, in this wall also velocity is 0, but at the top wall is moving with some velocity. So that, how that is creating the changes in all the domains fluid, you can see here. So it is shown from 1, so it is not total, but yeah, so ux uy, so we can analyze here. So this is one software named ParaView, where you can analyze whatever you have post processed. For the post processing thing you can analyze here. So it shows by the color map here shows that this is very high velocity, and as soon as, so because we know boundary condition is here with velocity, suppose velocity is 1, non-dimensionalized velocity we have given, and then it starts reducing from here and how it is reducing. We can do the vector thing here, and let me show you. Reduce everything. Let me not show it. It will take some time. Okay, fine. Have you got that problem? Why we are solving it? Anyone can comment. Lid driven cavity, yeah. Benchmark problem, yeah. There's a benchmark problem. So have you got the post processing of it? And as I am showing the velocity here, it's a velocity. So I want to show the this vectors. I don't know. This I'm using another kind of. Yeah, it's moving here. You can see it's so. Yeah, there is some problem in post processing. No, no, no. I will do it. So here you can see the vectors of velocity. These are the vectors of velocity. So in this, flow is rotating like this, and the top plate is moving by this velocity. This red velocity is shown by 1, means non-dimensionalized velocity 1, and others are moving in this fashion. So this is the visualization we will get, and scale it. Okay, let me do it. Fine, fine. It's fine with this only. So you understood the problem here. Means the solution of this. Solution is it's moving with some velocity and it is rotating all the flow here. And we can extract the center line velocity, and center line means the top plate center line from till the bottom, and how the sorry how the velocity is changing in all over the domain, and these are the vectors of velocity here. So hope everyone is getting it. So let's do it with our artificial viscosity problem or artificial viscosity method. Solution of this lid driven cavity, and if you can solve it, then you can solve the cubic problem also, which everyone is getting in assignment. And next will be solving this by simple algorithm. So these two will help you understand the problems. As you said, it's a benchmark. So till last lecture, what we have completed, let me write. We have completed all the prerequisites. Although it was not, I was not telling you, but it was all prerequisite for solving Navier-Stokes equation properly. So there was section by section I took the convection part separately. First I took the diffusion part, then I took the convection part along with steady, unsteady, differently, and 1D, 2D, all the problem I have taken, and discretization first I have taken in the MATLAB. So you know how to code it. So those were the prerequisites for solving. For CFT you can say, or for nuclear stocks. Okay. You can tell me other problems also so that I can take in next lectures, because I am not getting good feedback about like what you want to know. Then it will be easy for me to take those particular topics, because sometimes I take topics which is already taught in the class. So you can tell me whatever you need for assignment solutions, and then I can take it and it will help you directly. This will also help you while writing the exams. You will understand that these lecture will come into the picture, because assignment solutions are different, and these things, the basics are always come at first. Okay. So okay. Actually, that is why I started from basics, because sir haven't take it in. So I shared my like previous year's lectures with you all. I think you have it. So in that I took it in a more basic form, because I took it in a subjective way, not any coding, nothing. It was totally like the subject's way, or you can say the theoretical way only, nothing else. So if you have those lectures. Okay, what I will do is, yeah, I will post in that CFT presentation section only. Thank you. So let me write various equations now. Whatever equations we are using. For 2D scenario, let's write for 2D scenario. So first is the continuity equation. Then comes x momentum equation. Which is so Navier-Stokes equation is basically the representation of Newton's second law of motion applied to a fluid element. So that is I want to tell. This F is equal to ma is applied here. Then comes the first equation. So first equation is applied to u velocity, means the x direction. So which is del u by del t, del u by del x plus del u v. So I am writing the simplified form, conservative form, simplified. So del p by del x plus I am writing a form in which it is non-dimensionalized totally. That is why I am writing a Reynolds number here. So when you non-dimensionalize the equation, it comes that there is a term with Reynolds number in the equation, Navier-Stokes equation. So first term is this unstudied term. Why I am teaching this again, or telling this you again, it will be clear in some time. Convective term. Or maybe it is not clear, then it will be a revision for all of you. and then this comes as diffusion rate. Then comes this is V. Now comes del P by del Y. So here one thing everyone will understand, that there is no pressure coupling between this equation and this equation, or there is no coupling between when we move in the time. So that is what the basic problem in CFT, which is called the problem of pressure coupled equations. So yeah, I will just write and let me also write this whenever you read, because to now non-dimensionalized form this is. So now some very small. I think X momentum by momentum is covered. Now comes for better understanding, let's take it in one dimension. So I will again write it. So why I am doing it again and again, you will understand. Just keep patience. This is continuity equation only, and momentum equation will come, which is the first term here directly, no y, so del P by del x plus 1 by r plus by r. How we have discretized it? Let's see what happens in 1D. This is our point in which we need to analyze. This is our distant point, and then small d. And let's see the problem with pressure. So if you want to calculate here the del P by del x, or the pressure will be, so that minus del P by del x term will be what? How will you calculate? Minus del P by del x at this point will be P minus, so del P will be P capital E minus small e minus P small w divided by delta x. So it's a difference of these 2 points for calculation of pressure here, which is usually we do it the discretization. Then it will be Pw minus Pe by delta x. And how we will calculate the Pw? Pw is calculated as the average of these two. It's not always like that. I am just telling you the first method. So which will be PW, P capital W plus P capital P divided by 2 minus PE will be what? The average of these 2 points. P capital E plus P capital P divided by 2. Here P capital P will be taken off, and then it will become P capital W minus P capital E divided by 2. This term, pressure gradient term, which is called PG. Suppose if you will call pressure gradient term as PG. So it is like that. But suppose in a hypothetical, sorry. It's not statics. Correct. So it is delta x. So yeah, actually I don't want to tell you this. I want to main focus is we are getting the values PW minus PE here. So P's pressure is, suppose at point P the pressure is different. It's not constant in the whole domain or whole grid. Then what will happen? That is the main point of telling you all this. So suppose, let me write it. If P capital P's pressure is different, it's not constant, then what will happen? What is the problem? Suppose this is our grid, this is our grid, and here the pressure is 100. Here this is some hypothetical situation. I don't know whether how it is done or not, but this is, suppose it is possible. Pressure of this point is this, pressure of this point is this, pressure of this point is this. I want to calculate the pressure here. This I don't know. Then how will I do with this method? Is this is PE, this is PW, east west and present here. Let's calculate the value, and this pressure gradient will come as 50 minus 50 divided by delta x, which is 0. But is it 0? The pressure given by the 0 pressure gradient? It is not. It is not. It is not driven by the 0 pressure gradient, because here the pressure is 100. Then what will we do? Then comes the point of using staggered grid, in which we will stagger our grid. Stagger means we will shift our grid. So let's see how it is done. And let me also tell you about the one more situation in which velocity is not same. So, yeah, I want to calculate this term. Simple, same thing. Then same hypothetical situation, W. So U capital W plus U capital P. I am not writing all the things again. Minus U P minus U E by 2 is equal to 0. Delta x was there, but yeah, it will go. So what will come? UW is equal to UE. And suppose here velocity is 100, it is here 400, 400 here, 100 here, 100 again here. So velocity is something like this. Then what will happen? It will again, it is showing UW is equal to UE here. It is correct, but as we calculate del U by del x, that velocity here, as we calculate, it will also come 4, but it is 100 here. So yeah, if we are using non-uniform velocity field and non-uniform pressure field, then our our method, whichever we are using, needs some changes. So in reality, it is actually different most of the time. So this kind of situation is called as checkerboard situation. So yeah, I have some simply also we can tell it what is the checkerboard situation. So let me tell it mathematically. So this is my case from my notes. So I have done previously. So it is just integration that we do. Let us do the integration. So from west to east, this will come as PW. Let's forget about delta x. PW minus PE, and which is PW plus PE. I am writing it with fast because I have already told it, but I am just doing it mathematically without giving any example. So it's a we want to know this. EP. So, so this and again to another control in which every values any example I am taking. So in this control volume and this control volume, these both of both I have interpreted in the same way. So flow cross. It is a bit boring, but need to write it for others. Which is bit ironies for me. So the problem is interpolation has created this problem. Let's consider this again. What I will do is for velocity, I will have another control volume. So right now I am uh, suppose in this both the thing the velocity is different. So right now I am talking about only velocity, don't think about pressure. So here I will shift my control volume to calculation of velocity. If it is ux in the x direction, so I will shift this into in the x direction here. What it will do? Let's see what it will do. So this is what I am calling as shifting. It is called as staggering. The staggering my control volume to next step, or to that point in which I want to know the value. I want to know the value at p. So I will stagger my control volume for p to know my velocity. So my velocity at e will be this, in this direction. Okay. So I want to know this. Then what I will do, I will calculate PE minus PP. PE minus PP will give me exact velocity, or you can say the gradient between these 2 points, as compared to UE minus UW. So okay, let me write it. For pressure also we can do it. PP minus PE. I will do it. Velocity at point E is governed. I will go bit fast because I am writing a lot. In 2D, let's see 2D what will happen. 2D. I have this grid, I have this grid, I have this center point P, and this is my component, this 2D, so that, and I have this control volume, for which I am evaluating. What I will do is, from there, here this is point top. So this is one velocity coming from here. I will evaluate the velocity here and another velocity here. These are for ux. Separately, I will shift my, I will stagger my domain to this point. So I will do it differently. So this control volume is staggered in this direction for velocity in x direction. So this is my another control volume here, and you have velocity here at this point. For v, I will stagger this control volume to this direction, and we have vy here. No, it's not known. The points, like we want to know the velocity. Yeah, that is the point. That is why I am telling you. Like we find at the control volume center. Every value we will take at the center. P, V, T, everything. But here we are staggering that value so that we will, like when you apply for du by dx, suppose, okay, and you get that zero value, but it is not zero at that e point, then what will you do? So you want to know at e point only. here the velocity is 0, here 0, but here it is not 0. So here if it is not 0, then at the center we will get it as non-zero value or 0 value, but we want to get the actual value here. Actual value will be the difference between these two, and these two will be coming here, and the difference we want to know mainly the difference u at uij plus 1 minus uij. So this is actually uij plus I plus 1 comma j, and this is uij. Please, is it fine? Ui plus u, yeah. So what you are right now, what we do is ui plus 1 comma j minus ui minus 1 comma j by delta x. This kind of thing we do. But what I am telling is shift your control volume here, so that you will apply here this value, and this will give you actual gradient in the equation. So we will apply it into the equation, and the values will be taken at this point only, small u directly. So you are shifting. Yeah, staggered control volume. Yeah, exactly. So this is Vn and this is Ve. Fine. So this similar thing is I have something in mind. So when we take the unstructured mesh, a preferential orientation of grid lines along XYZ is there. So therefore, staggering of but in the particular direction is have no meaning. So what I want to tell is, in unstructured meshing there is no point of doing the staggering, because there is no orientation of that point. So it is only valid for structured grid. And there is another form of type of grid which is co-allocated grid, and grid of pressure and temperature and velocity are located in the same direction. So these my notes are completed. Let me just take due to the basic part where we were understanding that. So let me just start it. It is wasting a lot of time. I will not go into another details here, but just directly go to the problem so that you will understand the application of this staggering. Two points I want to complete in this. Pressure and density. Another is so do you know why, so it's not a question basically, I'm just telling you, do you know why we face problem while doing the incompressible flow equations? Because in this this is our continuity equation, okay? So in this equation there is no pressure term in the incompressible. But when we come to the compressible, it will come like this. So in this we have this density term, and it can be interpreted as differently. So here we can move forward in pressure, but in the incompressible flow we can't. So that is why we are introducing a artificial compressibility. Artificial compressibility is called as 1 by delta. Suppose dP by dt we have introduced. So as soon as our steady state is reached in any of the equation, then this will become 0. So automatically this artificial compressibility has no role. but we introduced to calculate the pressure till that point. So it's the basic of this. Okay, let me write this one. Today there is very less attendance. I don't know why. We are busy. Let me write it. Artificial compressibility method. So dp by dt plus dv by dx dv by dy equal to 0. This is called as artificial. Okay, I will upload it. You will understand by this. And there is no assignments and all for this. Just it is what why I will tell you. I am telling you because it will be like you can easily understand the staggered grid and later the simple algorithm like this. You will find it, I think, easily. But I still I will upload it into this where I. No. There is nothing about compressible flow. It is only incompressible flow. So these just wait. I will complete this writing this equation. I will explain it. So here, if you see this equation, these are the basic equations in 1D steady state flow. Okay. What I am doing is making it unsteady. Here I am introducing a term which is because this is not a compressible equation. In compressible equations, it is directly there. It is automatically there. 1 by rho, something like that. But here, introducing this will give us a pressure. Suppose this is, so how will you discretize it? Pn plus 1 minus Pn by delta T. This will give you P understand. Yeah. Huh? No. That is pressure term I introduced here. Okay, you understand. Yeah, there. That is why I said that there is in compressible equation there is density, but we can convert it into the pressure and write it. Yeah, any of equation. I am not going into that, but just understand this. Here we are writing dp by dt, and here we can convert it into the pressure for later time. So if you are moving in time, then how will you know that pressure, next time pressure? Because here there is no term of dp by dt. This is the basics of simple algorithm also. Okay, but there in simple algorithm we directly choose to do it by assuming some velocities and pressures. and then compare it with them, or compare it with this equation. So yeah, little by we will go bit by bit and then understand it for everyone. Mostly you will take these to one for a start. So this is just maintain by delta. What will be the this side I am writing? Okay. Pij minus Pij n. So this is the time term. So this is the partial derivative in time. So there will be no space. That is why only time. N is for time. Okay. Then comes qi plus 1 comma j, and this is u at eastern phase, and then comes uij at n. This is u at present point, up. So I am applying artificial viscosity thing here directly. I am not going for uw, I am going for up, which is uw is ui minus 1j. Okay. And similar for v, this upper velocity. So which is I j plus 1 at nth time step, and vij at nth time step by delta y equal to 0. So this is for this equation. Understood? Okay. So this is for one question. Today I will not touch relative cavity problem. Should touch it. So this you understood. Let's go for relative cavity problem. I'm not sure that it will be over in this lecture. Yeah, have you understood about a staggered grid and this problem, the pressure linked equations? Okay, let me complete this by here, and I will upload the next part in this only, but it will take some time. So let's conclude this meeting, and later we will meet for next time for relative cavity problem. So if yeah. No. I particularly for my research I use for finite volume method. For my research I use, so I am also working in high speed flows. So it is compressible flow basically. So I am using this FBM. So anybody using open foam is using finite volume. Yeah, open form is totally based on finite volume method, and I think ANSYS is also dealing with finite. I don't know about internals of ANSYS, but most probably it is dealing with finite volume. There are some particular you can say solvers in both of them and other solvers for FDM, but people don't use FDM. FDM is mostly used for understanding the problem. If you are writing a code, and if you are optimizing, linearizing, suppose this is bit advanced, but I will tell you. I am dealing with this rod. Okay, so I will discretize it, and after discretizing, if I have a computer with, suppose here we have six thing, six domains. So in FDM, uh, in FEM also it happens, but just telling in FDM. So if you transfer everything after parallelizing to a supercomputer, or your, suppose you have 4 core computer, you have divided this into the four parts, 2 3 4, and every part is supplied to 1 core of computer. So in FDM what will happen, like if you are solving a problem with FDM, finite difference method, then it is easy to scale that problem. So right now I have 4 core processor, next time I have 40, then I can easily supply to 40 core, and then 400 core supercomputer I have, then I can easily supply it to, not easily, but yeah, if I optimize my problem, and then the you can say the connection, uh, or you can say supply of information between two nodes will be easy there as compared to uh, FVM. But in both of them you can discretize, but linearization is easy in FDM. So both of them are having their own uses. But suppose you are using for airfoil or aeroplane simulations, you are doing aeroplane simulation, you will do in the compressible flow only, compressible flow regime, more than Mach number more than 0.3. Then what will you do is, most of the time people use FVM, because for integrate geometry you can't use FDM. It is very difficult to use FDM there in FDM, because there will be a grid problem, there will be a, here we have one domain, but there they don't have any domain. But most accurate solutions are coming from FDM. So yeah, you can use it for case where you are comparing your case. But here FVM also, if you directly solve numerical equation, which is called direct numerical simulation for turbulent flows, then also you can have a significantly correct values. I think I am going a bit, deviating a bit, but yeah, these are the things. So there is no sacrosanct way of doing problems, and people are using FEM also for material problems and all. It's coupled sometimes, but FDM I haven't seen much in research. There are people who are doing FDM for some geometries, for linearization and all, but not for big problems. Yeah, that textbook actually is very old. It is very old. Till then, what was the case is, every year we are getting more computational resources, more computers, big supercomputers and everything. So that is for, I think, hand calculation sometimes. Previously people used to have 2 MB RAM, everything like that. But right now our basic mobile is getting more than that. So this slit driven cavity problem I showed you, it is solved in few seconds, but previously it was not possible. Right now also turbulence problems we are not able to solve properly, or you can say easily, in this kind of scenarios. So for 1 second turbulent simulation, if I want to do it for in my desktop, it best desktop in the world, then it will take around some 400 years to solve. That is why people are using supercomputers. ANSYS is paid and OpenFOAM is unpaid. It's open source. No, there are other difference also. In OpenFOAM, you can write your own code, own C++ code, or you can change their Navier-Stokes solver, and you can change the boundary conditions and everything. In ANSYS, it is like a black box. So something is, you are giving something and it is giving something output. So that's another difference. So if you want to change code, if you want to make your own solver, then OpenFOAM is better. Or you write your own code or you use OpenFOAM. OpenFOAM, it will take some time to change the code, but yeah, basics things you can easily understand in OpenFOAM. ANSYS is very easy, and there if you want to implement something, then you need to write your user defined functions, and it is highly paid. Actually, it's very costly. ANSYS is very costly. People are using crack versions, but that is illegal, and you can use it for production runs and paper publishing and everything. Scientific purposes you can't use ANSYS if you don't have license. So you have to use the licensed version, and it is very costly. But in OpenFOAM it is totally completely free. You don't have to spend a single penny for that. Just download it and run it in your computer, and it is highly scalable. So if you want to run something in supercomputer, so here at IIT Kanpur, if I want to run something in OpenFOAM, it is extremely easy to run in supercomputers in parallel. But in ANSYS it is extremely tough to run, because you need a license there also, and it is shared between people. So, and there is a limitation for students for discretization in parallel, as I told you here in this. So in ANSYS only 4 cores you can use sometimes in a computer if you have the licensed version of students. So some people in industry, they pay much, and they can discretize it more. And one more thing, suppose you are starting a new entrepreneur, you are entrepreneur, you are starting a new company for CFD. So you download OpenFOAM. If you are producing anything from that, it is like free. You can say that it's my code. It's fine. Not OpenFOAM's code. If you changed it and started doing something else, and so you can say it's my code, and you can sell it sometimes. It's totally fine. And if you are using for your, suppose your simulation you are giving to some big company or a small company, or you started your entrepreneurship journey, so if you know the OpenFOAM, then what will happen, or if you know the coding, so if you supply them your data, there is nobody to question. But in ANSYS you can't supply. That's the difference, money difference. Yeah. Mhm. Yeah, there will be 3 indexing. You are absolutely correct. And for the boundary condition also, we have to think about different. Suppose, uh, so, but we need correct solution. If it is integrating that, then it is more complex, then it is fine, because every time we have to step for more complex problems, but more correct problem also. Suppose this is this problem. So what I will do, I will define pressure here, and velocity here or here. These points I have defined. Here I know the velocity, which is velocity 1. So this will be the like average of these two velocities. So suppose this velocity is u s, and this is another un. Okay, so un plus us by 2 will be 1. So un will be 2 minus us. This is the connection here. And for the for your question, suppose this is our pressures. Here we will define like this. Okay, I will discretize this. I don't want to cover it now. Just want to give a basics. Then what I do, I will show you one only. Nothing else. Because next time I will cover it totally and with the code, MATLAB. everything. This is our one grid and it's a center. Then this is 1 comma 2 and this is our pressure. This is another point. This is another point. These are another point. So these are for velocities. So these here also we will get it. Here also we will get it. So for this indexing is different for velocity. This is for pressure. Suppose it is 1 comma 1, 1 comma 2. So this for velocity we have to define 1 comma 1, 1 comma 2, and this is 3 comma 1 and 3 comma 2 or 2 comma 1, 2 comma 2, and this is 2 comma 1, 2 comma 2 for. So because it is MATLAB, so I am defining it in this way. But yeah, you have to define for everything. You have to define a different indexing, and it will help you also. So you are staggering this point to this point, this point to this point, something like that. Understood? Yeah, because we want to know the exact values. That is why we are staggering. Without that, there is no point of staggering. Some other questions you want to ask? Okay, from the assignments. Okay, let's meet next week. Okay, bye.